Welcome, squad. Today we're reading Physics for Scientists and Engineers, the 7th edition. I'm going to start off with the Section 5 opener. Just quick little read through of the paragraph so you guys can take a look at it. But I'm going to be reading it pretty quick. And I recommend, if you guys can take a look at this book online, check to see if you can find the PDF. Try to read it on your own. But if you don't have the time to do that, feel free to throw this video on 1.5 times speed. Listen to it while walking to school or cooking some stuff. And then we're going to follow in with the first chapter of this light and optics section, chapter 35. And I'm basically going to do a very quick 7-minute read through of the chapter to kind of show you guys what you can try to do before each lecture, so you can just see the information you're going to learn once before entering the lecture. I think it's very important, and this video is just a proof of concept to show you you can do it in 7 minutes. If you don't even have the time to do that, I have done it in this video. It is a little bit janky, but you can throw the video on 2 times speed, and you can get a summary of chapter 35 in like 3.5 minutes. So I hope you enjoy. Try it out on your own as well. And in the next videos, we're going to go through a deeper, more solid run through of this chapter and do a couple problems too. Light is basic to almost all life on the earth. For example, plants convert the energy transferred by light to chemical energy through photosynthesis. In addition, light is the principal means by which we are able to transmit and receive information to and from objects around us through the universe. Light is a form of electromagnetic radiation and represents energy transferred from the source to the observer. Many phenomena in our everyday life depend on the properties of light. When you watch a color television or view photos on a computer monitor, you are seeing millions of colors formed from combinations of only 3 colors that are physically on the screen: red, blue, and green, or red, green, blue, RGB. The blue color of daytime sky is a result of optical phenomena of scattering of light by air molecules, as are the red and orange colors of sunrises and sunsets. Damn! You see your image in the bathroom mirror in the morning, or the images of other cars in your car's rearview mirror when you are driving. These images result from the reflection of light. If you wear glasses or contact lenses, you are depending on refraction of light for clear vision. The colors of a rainbow result from dispersion of light as it passes through raindrops hovering in the sky after a storm. That is the introduction to part 5, and I would say that the most important sentence is this. We discussed the dual nature of light. In some cases, it is best to model light as a stream of particles. In others, a wave model works better. I guess another important sentence to outline is this. These images result from reflection of light. If you wear glasses or contact lenses, you are depending on refraction of light. And if you include this thing here that includes dispersion, then that is pretty much all of chapter 35. So here we have the beginning of chapter 35, the nature of light and the laws of geometric optics. And you can see it's broken down into 8 sections. The nature of light, measurements of the speed of light, the ray approximation in geometric optics, the wave under reflection, the wave under refraction, Huygens principle, dispersion, total internal reflection. So 8 sections, and I'm going to try to show you guys today how we can go through this fairly quickly. I haven't studied this type of physics in a little while, so I'm coming at it with a rusty, or I'm coming at it with a fuzzy memory. So I'm going to show you guys how I would read up on this. And it's good to read up very quickly before a lecture so that you have an idea of what the heck is happening and you have something to relate it to. So we're going to try to go through this entire chapter here in 7 minutes. I'm going to set a timer for 7 minutes here on my phone, and we're going to test it out.
In 7 minutes, starting now.
The nature of light and the laws of geometric optics. In the first chapter on optics, we begin by introducing two historic models of light and discussing early methods for measuring the speed of light. Next, we study the fundamental phenomena of geometric optics, reflection of light from a surface and refraction as the light crosses the boundary between two media. We will also study the dispersion of light as it refracts into materials, resulting in visual displays such as the rainbow. Finally, we investigate the phenomena of total internal reflection, which is the basis for the operation of optical fibers and the burgeoning technology of fiber optics. Okay, cool. Nice little summary. So we have section 35, the nature of light. We can just sweep through that. Before the beginning of the 19th century, light was considered to be a stream of particles. Okay, interesting. Most scientists accepted Newton's particle method. Newton, we know that guy. In 1801, Thomas Young, those dates provide the first clear experimental demonstration of the wave nature of light. All right, I'm just kind of reading the first sentence of each paragraph. Although the wave model and the classical theory of electricity and magnetism were able to explain most known properties of light, they could not explain some subsequent experiments. The most striking phenomenon is the photoelectric effect, discovered by Hertz. Okay, this is something different. Here's our first equation, energy of a photon, and it shows you E is equal to hf. H is Planck's constant. We studied this in chapter 40. Okay, sick. Let's move on, since we're going to see that later, to 35.2. So section 31 was a brief historical period and an equation we're going to see in chapter 40. Cool. Let me see how much time I got in my timer. 5 minutes. Okay, we spent 2 whole minutes on chapter 35.2. Let's move fast and see if we can get this. So measurements for the speed of light. Romer's method. We got a dude named Romer. Take a look at this picture. If we read it, it says figure 35.1, Romer's method for measuring the speed of light in the time interval during which the Earth travels 90 degrees around the Sun, 3 months. Jupiter travels only about 7.5 degrees. Okay, so Romer's method looks like he takes some speed differences between different planets. Cool, okay. We'll get into that a bit deeper later. Fizeau's method, let's look at Fizeau's picture here. Fizeau's method for measuring the speed of light using a rotating toothed wheel. The light source is considered to be at the location. Okay, so he's spinning a wheel, shooting a light beam. Then we got an example problem, measuring the speed of light using Fizeau's wheel. Okay, we'll come back to this, but here's a couple equations that seem important. Maybe we can take a look at those. T is equal to delta theta divided by omega. C is equal to 2d divided by t. Looks like velocity is equal to distance over time. Interesting. We'll keep that in mind. Checking the timer, we got 4 minutes. 35.3, the ray approximation in geometric optics. Okay, ray approximation, we have a picture here, a plane wave propagating. Okay, it looks like we have a bunch of rays, and that's how we can approximate light. They show us some other equations here. This picture is pretty interesting. It shows us 3 different examples. Lambda is less than. So when you have 2 less thans, it means lambda is much less than d. Then we have b, lambda is approximately d, and lambda is much bigger than d. And we have the rays doing kind of different things. Okay, so light can behave differently when it's passing through different apertures like this. Interesting. Then we have our first real equation. And if you take a look, it is yellowed out over here, yellow highlighted. It is the angle of reflection is equal to the angle of incidence. This relationship is called the law of reflection. Okay, this looks pretty important. And over here, you can actually see it. Basically, this image over here. According to the wave under reflection model, theta 1 prime is equal to theta 1. Okay, interesting. And when you have a bumpy surface, they reflect off of different places there. But pretty simple equation. Theta is equal to theta. The incidence angle with respect to the normal is equal to the reflected angle. Then we have another example, the double reflected ray. Interesting. We can take a look at that in more depth. Then we have some interesting examples. They show you that all reflective stuff like stop signs and bike helmets and stuff like that are a use of this double mirror. Interesting. So we got 2 minutes on the timer. Let's see if I can zoom through. The wave under refraction. Ooh, we have a more complicated equation here. Sine theta 2 is equal to sine theta 2 divided by sine theta 1 is equal to v2 over v1. And this is wave under refraction. Okay, reflection, refraction. Take a look at this example here. We can see a light ray is reflecting. Theta 1 is equal to theta 1 prime, the law of reflection that we saw earlier. And we have a refraction, which is light kind of bending into the medium. Interesting, we got a couple problems here. They give you kind of an example, I guess, with concrete and grass. The index of refraction, this looks pretty interesting. It is a definition. N is defined as speed of light in a vacuum divided by speed of light in a medium. Okay, cool. Indices of refraction, they give you a bunch of refractive indexes for different materials. It might be kind of difficult to go through this in 7 minutes. I have 1 minute left. Okay, here we got another Snell's law of refraction. Angle of refraction for gases. Cool, cool. Light through a slab. A bunch of interesting examples. Ooh, a prism. Huygens principle. This is the thing I didn't know. At this point, the importance of Huygens principle may not be evident. Predicting the position of a future wave from front may not seem to be very critical. We will use Huygens principle in later chapters to explain additional wave phenomena for light. Let's actually read what this is. All points on a given wavefront are taken as point sources for the production of spherical secondary waves, called wavelets, that propagate outward through a medium with seed characteristics. Okay, image, Huygens principle applied to refraction. Dispersion, all right. Total internal reflection, looks like another equation here. And optical fibers. Okay, and then we have a summary. Okay, so that was my 7-minute run through. That was rough, guys. That was rough, but we were able to get to it. I know I kind of spent a lot of time on the first sections. Maybe I spent like 2 whole minutes on section 1, even though looking back at it, section 1 was like 1 paragraph. And the second part of that paragraph was like, hey, this is going to be read in chapter 40. But we're just showing it here for you. So anyway, I'm just showing you guys that you can kind of do this very quickly. 7 minutes is quick. While you're brushing your teeth, you can zoom through this, or you can watch a YouTube video about it. But you can get it into your brain at least once before going to the class. So I guess in summary, I mean, here's the summary actually. Index of refraction. We heard that kind of quick. Like we saw the words and we saw this letter N. We got some concepts and principles. In geometric optics, we use the ray approximation. Okay, we read that at the beginning. Total internal reflection, that was near the end of the chapter. We didn't really spend too much time. Then it says the critical angle theta c. Okay, we did see stuff about angles. Here's the thing I remember most. Wave under reflection. The law of reflection states that for a light ray or other type of wave incident on a smooth surface, the angle of reflection theta prime 1 equals the angle of incidence theta 1. It's like basically the law of billiard balls or pool, the game pool. You shoot a ball, boom, it hits it, it reflects at that angle. That's exactly how light reflects off of a mirror. So pretty cool. At least from 7 minutes, if I can remember that one wave under reflection law, which is literally theta equals theta, like not really that much crazy of a thing. You can see the picture better than you can see the equation. I think that 7 minutes is worth it. You learned one concept, you're booling. Wave under refraction. This we didn't spend too much time on. But as you can see, this is a quick summary of what we went through. And you can do it in 7 minutes. I know I'm talking more than 7 minutes now, but you can quickly look and kind of read the first, look at the pictures, read the titles of the pictures, read the titles, check the equations out, read the first sentence of each paragraph, and try to get one of these down before going to the lecture. Then after the lecture, you can do a deeper read of the chapter, things that interested you, things you didn't really have time to cover, and you will find much more information and much more depth, of course, because you're spending more than 7 minutes on it. But you can for sure do the 7 minutes. Try it out. After this, there are some problems and questions, but if you just do this for one day, that quick 7-minute run through, you're already miles ahead of never taking a look at this stuff until the exam.